Hello, welcome to Astronomy. Today we're going to go over section 12.3 and 12.4 in the same video because 12.4 is actually a really short section and 12.3 is also kind of short, but there's no point in having a normal video and then like a 3-minute video. Just smush them all in the same thing. It'll be fun. Really excited about this section though because it's talking about black holes and those are really cool to learn about. So first let's go with the definition. An object from which neither matter nor light can escape is called a black hole. Okay, so matter and light cannot escape from a black hole. Already kind of weird to just think about. We don't really think of light interacting with things. It just kind of does its own thing and we just kind of let it, but an object from which neither matter nor light can escape is called a black hole. Here's kind of an explanation of how we can get to a black hole. If we look at the top left, we see a supergiant star. Even though those stars are massive and have a pretty strong gravitational pull, with regard to light, it's relatively weak gravity. So when the star is emitting photons or emitting light, the light essentially travels in straight lines out of the star. This is how light works with the computer you're looking at. This is how light works with the sun. This is how light works with the lamp that's in your room or whatever. Light just kind of goes in a straight line, not really bothered by anything. Now, once this supergiant star collapses, like last section, it can form a neutron star. And we talked about how dense those are. We talked about how a spoonful of neutron star could be, what, like 200 billion tons or something crazy like that? You try to squish 2 to 3 solar masses into a super small area. It has such a gravitational pull that if you see here, light actually doesn't travel in straight lines, it's actually kind of curved. Because the light is being pulled by this gravity so hard, kind of. There's actually a bunch of like Einstein relativity stuff happening. But the photon's trying to leave, but it's kind of being bent by this gravity. If we have a really massive neutron star, then the photons are really curved. They bend light a lot. And then the question comes up, well, what happens if we just keep upping the mass on this neutron star? And what happens when the light gets bent so far that it can't actually ever leave? That's how we get a black hole. So if a dying star has more mass than the maximum permissible for a neutron star, which is about 2 to 3 solar masses, not even the internal pressure of the neutrons can keep the star up. So last chapter we learned that when the star collapses, it hits that core, the core collapses into a ball of neutrons, and then neutron says, I'm not going to squeeze anymore, and it bounces back and ends up in a supernova. In the biggest of stars, that step doesn't happen. In the biggest of stars, that stuff gets squished, and the neutron says, I'm not going to, oh wait, actually I can't stop you because the star is so massive that it's going to squeeze all the neutrons so hard that it actually squeezes the neutrons into zero density, zero-ness. It's almost like punching a hole into the universe that no longer makes sense. If we go with Einstein's theory of relativity, then space and time is kind of like a fabric, and really heavy objects can kind of bend that fabric. But a black hole is a hole in that fabric, to where if you get a little too close to this hole in the universe, this object will go down there and there's nothing you can do to stop it. So right now we experience space and time as pretty much in a flat. That's not true, but like pretty much flat. But once you get too close to that, space and time stop making sense the way we think of and starts just curving straight into the nothingness that a black hole is. So there's a lot of myths that we're going to clear up about black holes in this chapter, the first one right here. If our sun were to suddenly compress into a black hole of the same mass, what would happen to the planet's orbits? Some people might think, well, since our sun turned into a black hole, it's going to turn into a vacuum and just suck up everything around us. But what we have to remember is that a black hole still has mass, and in this hypothetical, the black hole still has our sun's mass. So as far as we could tell, gravitationally speaking, nothing would change. Because right now Earth is orbiting the mass of the sun. If the sun is a black hole, the Earth is still orbiting the mass of the sun. We wouldn't get any light, that is true. But as far as gravity is concerned, gravity would not have changed. So we would still be rotating around the Earth. I'm sorry, rotating around the sun. Revolving around the sun. What's the word? Rotate, yeah, revolving around the sun. Okay, so surrounding a black hole, where the escape speed from the hole just equals the speed of light, is called the event horizon. So if we're talking about a black hole can suck up light, and then the question might be, well, how close can you get to it without being sucked in, right? And the answer to that is at the event horizon. Once you pass that, then you have to be going faster than the speed of light to get out, which you can't do. Once you reach the event horizon, then you have to be going the speed of light to get out, which we can't, but light could. All right? So this surrounds a black hole. Essentially the barrier, you can almost say, where the escape speed just equals the speed of light. You'd have to be going just at the speed of light to be able to escape. The distance from the center of a black hole to that event horizon is called the Schwarzschild radius, named after the guy who kind of came up with that. All right, so we can think of like how big is the Earth? Well, we think of the radius from the center of the Earth to the surface of the Earth. That's kind of what we're talking about here, from the center of a black hole to the surface of the extent of the black hole. Because it doesn't make sense to talk about the surface of a black hole, because remember, a black hole is nothing. It's a bunch of nothing in a spot of zero. So the distance from that spot of nothing to the point in which you have to be going the speed of light to escape is called the Schwarzschild radius. The star's entire mass is crushed to zero volume, and hence infinite density, at a single point known as the singularity. So in math, probably like in algebra or something like that, or in even in science, I know you learned, if you had me for 8th grade, you learned this. Density equals mass divided by volume. All right, so if you want to know how dense something is, you put its mass divided by its volume, and you can find it out. So for example, if it was, I don't know, something was 10 grams, and it took up 1 milliliter of space, that means the density is 10 grams per milliliters. Okay? So what black holes do, and why this like breaks all the rules, is because we say we put a certain amount of mass over no volume, over zero volume. And you guys learned in math probably in like 7th or 8th grade that you cannot divide by zero, right? You can't do this in math class. But in reality, we can't, but in reality this happens out there thanks to how massive these stars are. They hit themselves so hard that they squeeze all of that mass into zero volume. And they essentially divide by zero. So what happens when you divide by zero? You get black holes. That's what happens. We can't do it on our calculators. Our calculators cannot figure out what that means. Math doesn't work like that, but here's an example of real world where it can happen, where all the mass is in a single point of nothingness. Infinite density. So this question then shouldn't make any sense to you, because it's saying how many times larger is the singularity's diameter for a 10 solar mass black hole compared to a 20 solar mass. So this is twice as big. It wants you to think, oh, that means the singularity is twice as big. But remember, it takes up no space. It doesn't matter how much mass you have, it takes up zero amount of volume. It could be 100 solar masses, and the actual singularity takes up nothing, no space at all. Zero diameter. Doesn't matter. 0 inches, 0 feet, 0 miles, doesn't matter. It's zero volume, zero distance. It doesn't make any sense. So a couple more myths that people think. On the top, you see when a star becomes a black hole, its gravitational pull becomes stronger. That is not true. We already talked about that in the other question. If you're this dotted line distance away from either a star or a black hole with the same mass, you will feel the same gravity. Okay? Doesn't matter. What matters for gravity this far away is the mass of the object. So if the sun was replaced with a black hole, everything would still be rotating around, revolving around it just the same. Just for example, if you smushed the sun into a black hole, its Schwarzschild radius would be 3 kilometers, meaning it'd be 3 kilometers from the center of the singularity, which is I mean, it's just nothing, but from the center of the black hole to the event horizon. Only 3 kilometers. If you squish all the sun into 3 kilometers, or into infinite density, then the black hole would be 3 kilometers in radius. Which means if you were at that 3 kilometer mark, 3 kilometers away from this black hole, you'd have to be going the speed of light to be able to get away from it. And if you were 1,000 kilometers away, you would weigh 8 billion newtons. Right now you weigh 80 newtons. Another weird thing is the larger the black hole, the more powerful the gravity is near the Schwarzschild radius. Well, gravity depends on both the mass of the objects and the distance from the object. So, kind of strangely, this small black hole with only 1 solar mass, if you could stand right next to its event horizon, you'd be 8 billion newtons. This gigantic black hole over here with 1 billion solar masses, if you were this far away from its event horizon, you'd only weigh 900,000 newtons. So in some weird backwards thinking, these smaller black holes can kind of exert a larger force on you if you're outside the event horizon than the large black holes. Okay? Because you're closer to the center. Here you're really far away from the center. Here you're really close to the center of the singularity. Because you're so close, the gravity can be so much stronger. Because you're so far away, gravity is not as strong. And that has to do with how math works. The equations are more dependent on the radius than the mass. So the radius has a bigger effect on how much force you feel compared to the mass's effect on how much force you feel. I hope that makes sense. Since you're closer to the object, the gravitational pull is really strong. And even though this object is much larger, you're so much farther away, and distance has so much more of a play in this equation that you actually weigh less. So this is not true up here. The larger the black hole, the more powerful the gravity is. That is not true. It's the opposite. The smaller the black hole, the more powerful the gravity is near its Schwarzschild radius. This is what I was saying. This section's quick. I'm only 12 minutes in and we're already done. 12.4 will be done shortly as well. Black holes cannot be seen directly. You might not have put that together yet, but if these black holes are so large that light can't escape from them, that means if they're out there, we cannot see them. So then the question is, how do we know they're there if we can't see them? Well, last year we took the first picture of a black hole. What you're seeing is you're not actually seeing the black hole, you're seeing the radiation coming from around the black hole. As these different particles are getting sucked in, they start going super fast and they rub up against each other and they release some radiation right before they end up being stuck in this stuff forever. So we can actually map out this radiation, and that's kind of what we're seeing here. So a computer saw the radiation, put it into some way that we can actually visualize it, and then spat out this image, which is actually pretty insane that we're alive and being able to see that. One of the easiest ways we can actually find out if a black hole out there is with binary star systems. Remember, we talked about binary star systems being systems where 2 stars are orbiting each other. And it's possible that one of those stars ends up being a black hole. Right? If we have 2 stars and one of them is really big and goes through its life cycle really quickly and becomes a black hole, and the other one is still just chilling as a regular star, then these two will still be orbiting around each other, but one of them is going to be a black hole. We cannot see that one, but we can see the other actual star acting strangely. For example, it's now orbiting around a spot of nothingness out there. Another example is if those 2 stars are close enough, then the actual star will be giving off radiation that will be getting, and particles that will be sucked in to the black hole. So we can trace all those particles being taken to a certain point and then kind of disappearing. And that's how we know a black hole is right there. That's how we know that those two stellar objects are rotating around each other. One of them being a black hole, taking in the material from the other star. So we can trace these particles and this radiation coming from here. So we don't actually see the black hole, but we see the effects of the black hole. If a gravitationally bound binary system now contains one black hole and one red giant, which of the two original stars was more massive? Remember, we talked about the main characteristic that determines the life cycle of a star is the star's mass. So a larger mass star will go through its cycle quicker, which means if one's a black hole and one is not, that means the one that is a black hole was originally more massive because it already grew up, became a giant, and exploded long before the other one even went through its cycles yet. Okay? So the more massive star went through its life cycle, ended up as a black hole, and the other one is still going through its life cycle, which means it was smaller. So the black hole was originally more massive. And this note is kind of giving us a glimpse into what the next couple chapters will look like. Gas gravitationally collected at the center of most galaxies give rise to a central supermassive black hole with a truly stupendous mass. So at the center of galaxies, which we have not talked about yet, there appears to be these gigantic black holes. We can tell that because there's a bunch of things moving around them at ridiculously high speeds. Ridiculously high speeds. And the gases are being sucked in there really high speeds, and they're heating up and they're giving off radiation. Next chapter we'll be able to see a little bit more about this. This is kind of just like a preview as to, hey, look, these are also in the galaxies when we talk about galaxies. If they're rotating, they actually can start shooting out materials above and below. Thanks to a black hole spinning, it makes a bunch of electric and magnetic fields. So there's a lot of crazy stuff happening there. What is the best evidence for supermassive black holes at galactic centers? As I said, all that gas and those particles being sucked into the middle are going super high speeds and they're giving off crazy radiation. And the only thing that could be accelerating that gas so fast is an immense gravitational pull that would be coming from a black hole. And that is it for section 12.4 as well.